Good. So today's class, the idea of today's class is mostly to discuss another topic that I think is interesting to discuss with PBR. I won't code PBR today, as I said yesterday. I don't want to. I think that the PBR is quite simple to integrate, so it doesn't make much sense that I go through all the code and code the same on the engine. I think it's also interesting that you try to do it by yourself. But I'm going to code a little bit about the topic of today, which is something related to visual fidelity, how to make our renders as realistic as possible. And because this is more like a topic that maybe some people, it's hard to grasp sometimes, I think it's better that I just show it and I discuss a little bit about the topic on the code so you can see what I am explaining. Okay, as I said, it's not very complicated, but still, well, it's very, you have to build intuition, and building intuition could sometimes be a little bit hard. Okay, so let's go through the slides. I put them on the Aula Global, so you can go there to see them. It's about two topics. The first is linear space, and secondly is HDR. I put them together, although they are not exactly perfectly related. But I put them together because I think, well, they are very related. And also, when you're implementing one, it's good to implement both. So you are just adding the extra realism that we need on our renders. Okay, so let's start by linear space. I think it's interesting. Although this is, many people, when they render, they don't know anything about linear space, and you can live your life making renders without knowing anything about linear space. But they say if you know that you can have more realistic things. Okay, so what we want to achieve always is these super nice renders, very realistic. We know that achieving realism takes time. It's not straightforward. You have to add every single part of the chain to make it realist. You have to do it, otherwise at the end the image won't look perfect. Okay, so first I want to talk about perception, because linear space is something related to perception. So let's look at this image that you have now on the screen. On this image, there's three squares, red, green, and blue. And if you pay attention to these three squares, they are the like this is 100, this is 010, and this is 001. Okay, so this is the colors you will see if you put a maximum, the red level, the green level, or the blue level on an image. Okay, and if you are kind of observer or a person who pays attention, you realize something strange, which is that the red and the green, they are more bright than the blue. And this is strange, no? Because if this is the max blue, why we perceive more bright red and green? Okay, this is not an error of the image. I don't know if for you, any of you feel that they have the same brightness, but it should be quite obvious that they don't have exactly the same brightness. This is the first thing that is weird. And there's one explanation, which I don't know if this is the perfect explanation, but more or less it says that the pixels on our screen, first, that the blue is a strange color for our eyes because we have evolved in a planet where all the blue comes from the sky. Like there's a lot of blue color coming from the sky. And because of that, our eyes are more skewed towards ignoring blue, because blue is not a color that adds much information, because everything has a little bit of blue. If the sky is blue, it's emitting blue light, so blue is not super interesting. So our eyes are more interested about other colors, so that's why we pick up more red and more green than blue. And that's why when you go to screens, like if you zoom in on the screen of your cell phone, you're probably going to see that the pixel density is not exactly the same. There's bigger blue pixels than red and green, and that's because they need to put more intensity to blue to counteract the fact that our eyes don't perceive blue as much as red and green. Okay, so this is the first thing that is interesting to notice, is that something that's so obvious, like our eyes perceive red, green, and blue as the primary colors, is not so straightforward. And these kind of things, on the long run, it matter. Okay, and so as I said, when we were discussing here, these three colors, then you start seeing that our perceptive system is very important. We understand our perceptive system. If we just assume things like our eyes are perfect and they distinguish perfectly red, green, and blue, but that's not totally true. So we have to always keep understanding this perception system to make better renders. Okay, This is just one thing that I thought is interesting to talk about. This is not exactly related to linear space, but just as a first glimpse about how our perception tends to be more complicated than what we think of. Okay, so let's go for another topic, or the next thing. It's imagine I want to make a gradient. Okay, a gradient that goes from red to green. So I want to have on the left side of my gradient, I want to have all red, on the right side green, and in the middle, the tones that are in the middle, okay? If you want to do this with a fragment shader, you just render a quad, and that full screen quad, you put that using the vertex, I don't know, the X UV, then you have both colors, the pure red, you can see here 1001, and the green 0101. Okay, and you have these two pure colors, and then you apply a linear interpolation between both of them. Okay, using this linear interpolation from left to right. Nothing fancy. Okay, so you understand probably that on the left side we will have red, on the right side we will have green. Okay, so first question I'm going to throw to the class, and you can write on the chat, is: do you think that over this image the luminance will be constant, or the luminance should be different on some of the parts of the image? I'm talking about luminance, and you know the luminance of a pixel is the average of the pixels, okay? So, who thinks, or what do you think? Is the image is going to have the same luminance in every pixel, or some pixel will have different luminance? If you see here in the mathematics, the interpolation between these two values, for instance, the middle value should be, if you think that this is a 0.5, you do the linear interpolation between red and green, then the middle color should be 0.5, 0.5, 0.1. Okay, so do these middle pixels have different luminance? Yes, no? Can you type on the chat? I'm alone. Different. And can you tell me why do you think it's different? We can make the computation, by the way. It's like, let me see if I can open, I don't know, maybe I can open here. So imagine I have here on Google, I don't know. Do you have a calculator? 1 second. I can go here to open calculator. Yeah, there's a calculator here in Windows. Okay. So yeah, I see, because it depends on the UV. But let's think about it, okay? So we have a value that goes from on this left side here, it's 1, 0, 0. On the right side, it's 0, 1, 0. Then what's the luminance of this pixel? Who can tell me? For Adria, can you tell me what's the luminance of this pixel? Or anybody who wants to type on the chat? What's the luminance of a pixel that is pure red? This is pure red. Nobody wants to type. What's the luminance? Do you remember what's the luminance? No? You studied luminance a lot in the course about image processing. So if you don't remember what's luminance, luminance is adding red plus green plus blue. Wow, super complex equation. So the luminance here is 1. The luminance here is also 1. And I'm saying if we do a linear interpolation between these two images, is the luminance going to vary over this line? We can try, if you don't know intuition about this, you can always try to say, okay, let's find the color in the middle. If it's the middle, it's going to be a linear interpolation of 0.5. So it's going to be this 0.5, this 0.5 added together. So it's going to be 0.5, 0.5, 0. And we compute the illumination, we find it's 1. Everybody follows me here, because I feel like I'm talking something super complex for you that you don't follow me. And I think it's super simple. So, okay, illumination, the most basic thing is how much bright does it has, okay? So as I said, if we do a linear interpolation, brightness shouldn't change, okay? Because we are making a linear interpolation between 1 and 1. And if you do the linear interpolation between two values that are the same, you are going to always stay in the same. And this applies to any value here, because it will be 0.75, 0.25, 0. So if you add these values, it's also 1. Okay. So linear interpolation shouldn't change ever the illumination. So for those of you who say it's different, no, it's always the same. Okay, cool. Then go back to the slides. I'm going to show you a gradient that's using this formula. And if I show it to you, what we get is this. Okay, so next question is, do you perceive that this image has a constant illumination, like luminance? Because if you check this image, I don't know you, but I don't know also if you're watching in your computer or in a projector or whatever. But when you check this image, it should be fair obvious that this part here looks more bright. This part looks here more bright, this part, but this part looks more dark. And that's super weird. Like, why is the illumination going down? If I'm interpolation to values, I should expect the illumination to keep constant. Like, this area here has to be as bright as this area here as here. The color has to be different, that's for sure, but the bright has to be exactly the same. And I could ask you, what do you think this is happening? Or what, you have any kind of intuition why interpolating between two colors that has the same luminance is going to have a totally different luminance? But I know that you probably won't. If anybody wants to throw any possible idea, I'm always glad to listen to. And I also like to see that you are trying to use your brain to think about these kind of problems, because this is kind of things that if you don't pay too much attention, you can do this, you can see this, because I've seen this in the past before I understood why. And I always felt like this looks strange, but I never delved very deep into this topic. And now I know why. So, okay, I should have asked why this happened, or at least try to construct some intuition about it. Okay, so the solution to this problem, because I can see that nobody wants to try to guess anything, is linear space and gamma space. What's that? There's this thing called the Fetch's law that is important when you work with anything related to perception, that says that the relationship between the stimulus and perception is logarithmic. This logarithmic relationship means that if a stimulus varies as a geometric progression multiplied by a fixed factor, the corresponding perception is added only by an arithmetic progression, okay? The additive constant amount. Okay, so what does it mean? This is a fancy way to say that we don't perceive changes in our brain the same when the change is in a like, for instance, I always put this example. If you have if you want to buy something and the object costs €1, okay, and you know that the price is €1, and then somebody is, and you go to buy it to the shop, I don't know, could be, I don't know, a ticket for the metro, I don't know, and in the price, instead of being €1 is €2, you're going to be pissed off. You're going to say, hey, wait, it should be €1, and you're charging me €2. That's double. That's unfair. But if you're going to buy a house, and the house is, I don't know, €300,000, and the guy says, no, it's €300,000 plus 1, you're not going to be, whoa. You're ripping me off. This is not fair, okay? Because you understand that €1, when something costs €300,000, is nothing. But when it's €1 over €1, it's a lot. Okay, so that's a way to understand that we work always in relative. We don't never work in absolute values. The problem is not that something costs €1 more. The problem is that it costs double. And our mind always works like that. Not only when we think about stuff, also when we perceive stuff. If we have an amount of energy, also another way to see it, like if we have a light bulb that we can connect. So here we have a light bulb, okay? And we connect it through some wires to some electricity, and I pass through this electricity an amount of electricity, I don't know, 3 volts, I don't know anything about electricity, so this is my 3. This is going to shine, obviously. But if I pass another volt more, so 4 instead of 3, obviously this is going to be brighter, okay? But the amount of brightness, this difference from here to here is adding 1 volt. We will perceive it as a little bit more bright. But if instead of being 3 volts, we have, I don't know, 50 volts, and we pass another volt here, this difference, which is still 1 volt, you will see the light exactly the same. You won't perceive that there's much bright now. Although here you perceive a lot of change, and here you won't perceive any change, okay? Another way to see this, if you want, like if you're in a dark room and you take your cell phone and you switch on the screen of your cell phone, you will see a lot of illumination of the room, obviously, because the cell phone emits light, or even if you switch on the flashlight. But if you go to the to a very bright place and you switch on the light of your cell phone in outside during the day, you won't see any difference on light, because perception is totally related to logarithmic scale. So the more you perceive, the more energy you have to put to perceive more. Okay, so the bigger is the perception, the more energy you have to put to change it. Okay, and this has been known, not only applies to light, it applies to also audio. This is why we use the decibels scale when you want to work with audio, and it even applies to other things on our body. I mean, our brain works totally on a logarithmic scale. It doesn't work in a linear scale. Okay, cool. And what does this has to do with rendering? So imagine I want to make an image and I have this, like, as I said before, I have something similar to this light bulb I was talking before. So I have a light bulb, okay, and I can plug it on some wires, and I can pass 2 voltages. The maximum voltage this light supports is, I don't know, 10 volts, okay? And the minimum obviously is 0 volts, okay? So I have to map different values. I have different grays, so I have different grays, a gray scale here. So imagine that I have like a palette of different grays, something like, I don't know, I cannot replicate it very well now, but imagine I have like blacks here and grays here and lighter grays here until it's white. Okay, so I want to map them to this light. Okay, so when I don't want any light here, what I will do obviously is say this is 0 volts. Okay, and when it's white, or the maximum color, imagine that this is the purest white, we understand it's probably going to have to go with 10 volts. Perfect. But what happens with the tones in the middle? Like if this was, for instance, the middle color, you will expect that if this is the middle, okay, the middle gray, the gray that it's halfway between black and white, you will expect that for this one, we will use probably 5 volts. But as you remember, I say this is not how our perception works. If you do that, you're going to see that all the colors tend to be changed, and this scale won't look like a regular gradient. You will have something more like this. Okay, in this image, you can see that the darks are almost nothing, and all the rest are bright colors. There's no much dark grays. All of them are on the white area. Okay, and that would be like, oh, damn it. I mean, I wanted to map some brightness and to have a more linear scale, and instead I have this totally ugly scale that doesn't look linear. Okay, it doesn't look like a gradient that goes from dark to white on the same proportion over the distance. So this is a clear way to see that our perception is not linear. Okay, so okay, and how is this a problem? Well, this is a problem because if, for instance, you want to map values of intensity of an image, like have different grays, and I want to map them to our file. Like remember, like I'm going to go to GraphToy here. Maybe it's going to be easier to see it. Remember that this website is very useful when you want to map things. So imagine we have a classical function of linear, a linear mapping. So in this function, let's imagine that we want to see something like this. I'm going to put it like this. Okay, so we have 256 different values. Okay, from 0 to 255, okay, and if we map linearly, 125 is going to be 125, okay? So you can see if I put the mouse here below, you can see the mapping. So you can see here is 125 by 125. So it's a linear mapping. The same value enters, the same value comes out. But obviously, when we store data on our computer, because we are using 1 byte to store colors, we usually have only 256 different values. So in reality, what we have is more something like this, okay? This means that if I have a value between this number and this number, for instance, this is 85, this is 86. So if I have any number between 85 and 86, so for instance, 85.5, when you try to map it, it's always going to be mapped to the lowest possible value. So in this case, it's always going to be 85, okay, because we are removing the decimals, okay? This is regular when you want to map a decimal value to an integer, or when you're, in this case, to a byte, okay? But if we wanted to have fix this problem we have before here, one solution we can do is, okay, instead of using the half, like if I want the half intensity, I know that 0.5 is not half intensity because I can see here 0.5 is this color, and this doesn't look like I'm in the middle of of white and gray. It looks totally like more whitish. So I can try to find, okay, what's the color that is half between black and white? And it's going to be probably, I don't know, this color over here. So I can check which value is this one. I don't know, it's 2, sorry, and it's stored 0.2 instead of 0.5. So then when I have a lot of gray colors and different values and I want to map them, I can do that. But what I'm doing now, if I do that, is I'm pushing the values to like more values to this area of the possible values. So imagine that this is the 0 and this is 255. I'm pushing all the values down. So that's not good, because if I don't have infinite precision, which I don't have obviously because we are working on integer values or byte values, if I do that, I can map this so you can see it. What I will do, I can do something like this. This is similar to what I was talking, which is, well, sorry, I can show it to you maybe better here. So if I have x, but I square it to something, sorry, it's disabled. Okay, what you get is, I'm going to put here also something like this. So I'm pushing all the values. So for instance, any value like 5, I see which value it is 2. You can see here that when I go to search for 5, it has become 2. Okay, here you can see down. And this value 10 has become 9. Sorry, 10 has become 3. So you can apply a curve that instead of being linear is going to push all the values a little bit to the left. But if you do that, on the long run, we have a problem. Let me show you what's the problem, because you can see that every value, the jump is going to be, well, sorry, I'm going to show it better if I do this now. I'm going to take this value, apply it to something, floor it, because we are removing the decimals. I'm going to undo this conversion, because when we want two values back, I have to undo this conversion. To undo this conversion, I apply the opposite, okay? So if you do that, you're going to see that you are rounding the values, okay, as you were doing before, but if you go closer to 0, the closer you go to 0, you will start seeing something, which is the size of these steps is bigger and bigger and bigger. You can see here, okay? This means, so you can understand, that the precision you have on the bright areas is bigger than the precision you have on the darker areas. And that's bad. You don't want never to have less. Some colors have more bits and other colors has less bits. I mean, what I'm trying to show you here is if you are trying to map a linear function into non-linear, you are losing resolution of some of the data. Okay, and you're losing resolution not evenly distributed. You're losing in some areas, which is bad, because you mean that in areas where the image is darker, you will see more artifacts. It will look worse, way worse, than areas where it's brighter. Okay, so how can we solve this? This has been a problem from the very beginning, that when people wanted to store colors, intensities in images, when they have to store, I don't know, JPEGs, PNGs, BMP, whatever, and they face always this problem. And this is, as I say, this is not a new problem. This happened from the very beginning, okay? So we have a precision problem. If you do this, you will see, I don't know if you can see here, but the gradient is not so smooth. You will see like there's jumps on the gradient. There's areas where it's very, very, like there's not so many shades between two values, and other areas where there are more shades. Okay, so we are losing precision, and this is bad. And this is something that you may see in an image if it's not well done. Okay, so how can we solve this? Some years ago, when people started building their first monitors, they thought about this problem, and they come up with an idea that is very interesting. The idea is, hey, why instead of working linearly, which doesn't make any sense, we store the image not linearly. We store them using this curve that tries to maximize perceptivity. So that means that the colors where you perceive more, they have more bits, and the colors where you perceive less, they have less bits. So at the end, is like you're distributing better the bits or all the possible values between 0 and 255. And so that works for perception. You can do this, but the problem is that if somebody tries to see this image and doesn't know that this image is not linear, when they try to map it to the screen, the image is going to look horrible. So the thing is that the creators of the monitors that we are using today on any screen, they are aware of this. And they say, it's okay, because we are going to apply the opposite function. So you have to store the image in this way of mapping the values of intensities of light. And the monitor is going to do the opposite. It's going to read this as is not linear, and it's going to apply another function. And because I am applying this other function, the output is going to look linear. Okay, so this is nice because that means that we can use better bit encoding for any image. Okay, and the monitors will have to know how to decode it. And all the monitors have a gamma. That's usually, we usually talk with 2.2. This is the gamma. This is the function that when you do POW of one value to 2.2, you get this curve, or you do the opposite, 1 divided by 2, you get this other curve. Okay, so this is a trick that any image format that you ever use, any application that has images on the screen you ever use, they always map colors in gamma space because they know that your monitor is going to apply the gamma. So what you're going to see at the end is an image that it looks linearly. Okay, as I said, this is a trick we use to be sure that the image looks perfect. Okay, and if everything goes well, you should see this kind of gradient that is very smooth. It goes directly from one gray, black to white, passing through all the grays in the same amount of area. Okay, this is our goal. Okay, so why all this fuss, or why should we know about this? Because when you're mapping values like this, okay, so think about it. If you have something like all the possible 255 values, you can see that from 0 to 0.2, which is a bit the area where it's darker, we're mapping almost half of the bits of our byte. We are using half of the precision only to store from 0 to 0.2. Okay, which is good because we perceive a lot here on this range of intensities, and we do not perceive so much. Because we do not perceive so much here, we are going to use less bits. You can see that this range from 0.8 to 1 is going to be mapped between 124 and 255. Okay, so here we are using 128 possible values, and here we're only using 20 possible values, and that's good, as I said, because we can see much more here, this range of intensities of light, than this one here. And as I say, what is the problem here? The problem is when we operate. Imagine I have a gray, and I assume it's if I have a half gray, which is 0.5, and I have another half gray, which is 0.5. If I add both half grays, what I will expect is to have white. Okay, imagine the perfect half gray, like it's perfectly between white and black. In reality, because we are working on gamma space, I don't have 0.5. I have 0.4, 0.2 probably. The 0.2 is the half gray. Okay, the perfect half gray between white and black. So if I add half gray with half gray, I don't get white. I get another gray. Okay, and that's a problem because I was expecting something like this: half gray plus half gray is white, and what I get is half gray, it's something, it's another gray. And that means that when you operate, you are operating in gamma space. And remember, I always say that the light is additive. If I have one light and I add another light, I have double the light, so I only have to add them together, like mathematically it's addition. But that only applies if the light is stored in linear space. But we are not in linear space. Everything you have been computing until now, every single shader that you have coded, it was never in linear space. It was always in gamma space, okay? Because when you load images, they come in gamma space. When you send the image from the shader to the screen, they are in gamma space because that's what the screen is waiting for, okay? So because everything has been in gamma, all the operations we have done are wrong. And that means that the colors are not exactly the colors that it should be. Here's an example of two images. This is when we compute the n.l in gamma space, we get this. But if you compute the n.l in linear space and then you apply the gamma afterwards, you will see more like this, okay? And I know that some people may think, no, but this looks more realistic, more obvious, like the gradient has to be smoother, while this looks strange because the gradient suddenly changes very fast and goes to dark. But I will show you later that this is correct, this is wrong. So this is what you have now. If you do the n.l in gamma space, it looks like this and it's wrong. If you do the n.l correctly, it should be like this. So how can we operate? Anytime you have a value that is in gamma space, we have to convert it to linear space. Any value that is in gamma space, we convert every single value to linear space. Then we can operate, and at the end, when we are going to throw this value to the screen, we have to go back to gamma space, okay? So we need these two functions. We have function to convert from gamma to linear and a function to convert to linear to gamma. If you have this, you can operate and you are not doing any error on your computation of the colors, okay? So any image format that you use is always working on gamma. anytime you use a color picker, any application that lets you pick the color, you are picking it in gamma space. If you have any doubts, I recommend you to check it, and you will see how when you pick the grays, it's never picking 0.5. It's always taking something else. Okay, so this is why we have these kind of images where you can calibrate the gamma, because some monitors can have different gammas, and you can calibrate it using some sliders and sometimes. Okay, and this is a problem. For instance, because as I said before, every image that you have used comes in this gamma space. By the way, the gamma space usually is called sRGB. Okay, and you can see that, for instance, if you try to save an image on Photoshop, this is a screenshot from Photoshop, you will see that allows you to store in this perfili CC sRGB, and this is the standard that you're using. Okay, every application, when you store, by default is going to store in sRGB any image. Okay, and it's important because besides that, when you want to operate, as I was saying before here, you have to know how to operate. There's also problems inside the GPU. For instance, remember that we were using min maps. Min maps, by default, it's an average of the pixels. An average means that it's adding the neighbor of every pixel and doing a division by the number of pixels. If you do that and you are not in linear space, you're in gamma space, you are doing it wrong. And that means that when you generate min maps on the GPU, most commonly, those min maps are darker than what it should be. You can see here in this image, when we have half red, half white, half black, the more min maps we are using, the image tends to be darker. You can see here suddenly it becomes dark. Because when we join the average, as I say here, the problem is adding these two values. It should be half between, and it's another grade that is not supposed to be that way. Okay, that's not a problem, because GPUs has a function that where you specify a color. You can say, hey, this color, by the way, comes in sRGB. It doesn't come in RGB. And if you say this to the GPU will understand if in any moment it has to operate, it has to convert to linear space, operate, and store back to gamma space. Okay, so all GPUs support this. By the way, the engine we are using, I don't use this, so that means that all the colors are wrong and the min maps are wrong. Sorry, but well, I have to change my framework to be sure that when you load an image, it uses this format, but this format is not supported by all the graphics card, so I didn't want to add anything. As you can see here, if you correct this error, when you generate the min maps, when the GPU, you upload an image to the GPU and the GPU generates the min maps, it understands how to do it well, and you can see how it looks more natural. The intensity doesn't suddenly plummet to dark. Okay, it stays on the good color. Cool. Okay, I understand. Sounds strange. This is why this topic, if you are not used to these kind of things, it can be very annoying when you start working with gamma spaces, because it's like, whoa, how do I know what's in gamma space? How do I know what's not in gamma space? It takes time, okay? And the problem also is that the change here is very subtle. If you don't pay too much attention, you don't realize if something is not linear. It's just that the image doesn't look very good, okay? So, how we can compare between gamma space or not? Currently, all the monitors use a very simple gamma function, which is the POW, okay, the elevate to some base, okay, and here you can see the different curves for different POWs. So we are usually using the 2.2, this is the standard, although some people use the 2.0 because it's cheaper, because to compute the one number elevated to 2, so 2.2 implies more computation that elevated to 2, which is just multiplying the number by itself, okay, this is just POW of, is the square of some value. But well, usually if you don't care about this, you can use 2.2. So if you want to go from gamma space to linear space, you have to apply this function here. The gamma, you pass any color, here is supposed to be a color, and you're going to POW by this 2.2, okay? And if you want to apply the opposite, you want to go from linear space to gamma space, you apply the same, but 1 divided by 2.2, okay? It's not cheap. I mean, using POW is usually not cheap, but it's not something that you're going to do a lot, because the idea usually is that you try to, any value that you read that is not in linear space, you convert it to linear space, then your shader is going to be exactly the same, because everything is already on linear space, and at the end, if you need to store it in gamma space, you store it in gamma space. If you're going to store it in linear space, you can store it in linear space, and at the end of your pipeline, you go back to gamma space, okay? So here, this is an example I showed you before. This was the gradient I showed you before. And this is the gradient if I apply the right gamma correction. So here, as I said, I interpolated between the colors in gamma space and then, sorry, in linear space, and convert back to gamma. You can see there's a huge difference. In this gradient here, you can see how it goes from red to green, and the intensity stays the same. Here you can see some yellowish color, and more or less the intensity is very similar. Here on the other side, you can see in the previous one, the one we interpolated in gamma space, you can see here it goes to brownish, these darker areas, and it goes back again to bright. Okay, so you can see how here there's a huge difference between the luminance of these pixels. This is the right way to do it, this is the bad way to do it. Okay, so yeah, so just so to see how important it is, for instance, iOS, the operating system of iPhone and iPad, there's a lot of blurs that they do when you, I don't know, you want to blur the screen, on when you drag the finger down, it blurs the screen, or when you are doing some features, and they were doing the blur wrong, and they didn't realize that they were using on gamma space, not in linear space. I remember there was an update like 2 years ago where they fixed that, because it's a common error many of the developers that usually do. Anyway, you have problems understanding this and you struggle with this topic, I recommend you to see this presentation from Naughty Dog, where they tackle this topic, and they have a lot of nice images to explain this problem. Okay. And as I said, if we do it wrong, this is the n.l when you compute the light using gamma space, and this is when you compute it in linear space, and then you convert back to gamma. Okay, as I say, you can see there's this strange jump between bright area and dark area, which you may think it's wrong, but if you go to a real photo, you will see that it's right. In this ball, you can see this is a real photo. You can see how suddenly it goes very dark. Suddenly, the area where the gradient happens is super small, which is, it tends to be more online with the idea that we were talking. Okay, so it's kind of counterintuitive. You may think that this is the right one, but if you take a picture, you will see this is not the right one. This is the good one. Okay, so that's why we always have to work on linear space, and it's easy to spot when you have like a sphere or something on a 3D render if it's working right or not. Okay, so how we put this on our pipeline? It's not so complicated. Okay, first of all, you have to be sure in which moment you have to store in gamma space and which moment you have to store in linear space. Okay, remember what's the problem of storing in linear space. If you store stuff in linear space, you're wasting bits because you are crunching a lot of data in less bits, and that means that you are going to have artifacts. I will show you an image later. But if you store it in gamma, then be careful, because if you're going to add anything to that value, you're probably doing it wrong, because you're operating in gamma space and doing operations mathematically in gamma space, which is wrong. Okay, so any moment that we have to read a color, I would recommend you to do this. You read the color, and then you convert it from gamma, because all the textures are going to come in gamma space. You convert it to linear space. You apply this function, boom, you have the color in linear space. Just one extra line. Okay, and at the end of your render, when you have to do all the processing or whatever, you do the opposite. Okay, most engines, they do this. They always work internally in linear space every single step of the pipeline, and at the end they have a shader that is going to read the color in linear space, convert it to gamma space, and show it to the screen in the very last step of the render path. Okay, so at the end you always have to convert. You can have a shader that converts the output, the final output, to gamma space. Very important. If you do convert to gamma space, you're going to see that the colors look very brown. They will look kind of very grayish, and it's very important they convert it back. Okay. But what happens when we have a texture that is not perceptive? For instance, this image here, this is a height map that says which areas of a pixel are higher or lower. Or for instance, this image here, which is a normal map. Okay. We're used to see the normal maps. I understand that okay, every pixel says which this is oriented to the up, to the right, or to the front. Okay, but are these images in linear space or in gamma space? It depends. When somebody creates an image like this, usually he understands that these images don't have to be perceptive. These images are not created to be shown on the screen. They are created to be used for algorithms to compute the final color. So that means that they understand that it doesn't matter if this is, I mean, they don't need to put it in gamma space, because these images are not created to be seen. These images are created to be used as values on an equation. So they tend to be linear. I mean, height maps, normal maps, occlusion maps, they usually are linear unless the person who created says otherwise. So you don't have to convert the normal maps or the height maps or the occlusion maps or the metallic roughness images on to linear space, because they usually are already in linear space. Okay, only those colors that have been created to be perceived are not in linear space. Okay, and the problem is that if you store everything in linear space, for instance, when we are doing the ferret pipeline, remember that in the ferret pipeline, we are storing to every JBuffer uses an unsigned byte per channel component. So for every component of color, it's only using 1 byte. And then we have the problem again. If I read the albedo, and the albedo is in gamma space, and I convert the albedo to linear space, and I store it linear space on the GBuffer, I have the same problem. I'm wasting bits. And if I do that, you will see that when you try to reconstruct the color, you will see that the colors are all destroyed. As you can see in this image, that there's less possible values. So there's like crunched the colors. So it's important that we only convert to linear space when we are going to operate. Okay, but the buffers don't operate with the pixels. They just store them, and you are going to operate on the illumination pass. So on the illumination pass, you have to linearize, but not on the GBuffers pass, because we want to keep all the bytes as close as possible to the original values. Okay. But you can fix that. Is instead of using one unsigned byte, you use like half float or floats. GPU support that. You can store values to half floats, which are 16 bits, or floats, which are 32 bits per color channel. Obviously, the more bits you use for the color channels, the slower it will go, because it needs more time for accessing this data, because it's more like 4 bytes bigger every number. Okay, so we always try to avoid going to these values if it's possible, but for the next part of the presentation, you will see that we need to do this. Okay, so here this is a very, very important tag. One of the more important tags about this topic, is called the importance of being linear, and it's done by NVIDIA. And they put this in presentations like 10 years ago. And from now on, everybody understands that if you want realism, you have to work in linear space. Every single shader I've seen, they always have lines that say, oh, convert from gamma to linear. Okay, so super important. Okay, next topic, SDR versus HDR. And I put them together because you will see that there's some similitudes here. Okay, so SDR stands for standard dynamic range, or you will see sometimes on low dynamic range. And the idea is that usually every monitor that you have seen in your life, when they have to store colors, they always use an unsigned byte per color channel. This is the more standard format, okay? Unless it's specified otherwise, every single image that you have ever seen, every photo that you usually send through any platform, uses only 1 byte per color channel. Why? Because we have enough colors to cover most of the perceptive range, and if we apply the thing we say before about gamma space, 1 byte is more than enough, okay? Here, by the way, you have like this kind of images that there are many colors that don't lie inside this possible low dynamic range that we are using usually, and that means that, well, this it's not the same when you see an image on a screen that when you see it in real life sometimes, because you will see that the colors are totally changed. Okay, because, well, we're transforming to color spaces, and color spaces are not perfect, and also when you want to display back this image on the screen, also there's some conversion going on there. But as I said, we are always using an unsigned byte. Okay. And it's fine, because this monitor that we're seeing now only supports from 0 to 255, or if you want to work in normalized, which is better for our minds, 0 to 1. Okay. The problem when we work with 0 to 1 is that if any value is above 1, okay, it's going to be clamped to 1. So here you can see, for instance, you have different intensities. If any intensity goes beyond 1, okay, boom, it's going to be clamped. So it's going to store 1. Okay. And that's good. I mean, my monitor doesn't support to render brighter pixels than 1, so it doesn't make any sense that I have to support, unless you have a special monitor that has a special LED system that can bright super bright, and then maybe. But most of the thing, this is fine that we clamp from 0 to 1, because we don't need colors that are brighter than white. Okay. Although we understand that there are colors brighter than white. I mean, if I look at the sky and I look at the sun directly, my eyes are going to burn. And this is because what I'm seeing, it's very bright. It's so bright that it goes way beyond my perception, and also is destroying my retina. Okay, so we say that the colors go from 0 to 1, and we say the maximum illumination is white, but you have to think that there are whitest whites, like there's brighter whites, okay? It's just that we have a limit, and we say, or whitest white is the one that is on the center here, and that's it, okay? Cool, but there's some problem about that. The problem about clamping is that in some situations, and when we are working with colors like we are doing on our render engine, there's some situations where we want to know if one pixel is whiter than the other. And I'm going to show you this with the WebGL Studio editor. Okay, so imagine in this image here, I have two cubes, okay? And these cubes are, I'm going to put them, they're white. I'm going to remove the lights of this scene. So this cube by default is white. I'm going to create another cube here. Both are white, okay? But they are not exactly the same, because while this one is regular white, this one here is more like a incredible white, like 10 times whiter. Imagine that this is more like a light bulb that is emitting a lot of light, okay? So in this case, if I go to the material and this says, which is the color of this object? I'm going to say, it's not only white, but it's super white. I'm going to multiply by 10, okay? Ambient says, sorry, no, not this one, sorry, not this one, this over here, okay? But as I said, now they have different colors. This is white and this is ultra mega white. But at the end, when I see it on my screen, they just look white. They exactly look the same, okay? But imagine that when I'm doing this, I have also here another object, which is a plane. Okay, I'm going to try to put it, let me see if I can put it closer to the camera. And I'm going to rotate it a little bit, so 1 second. And this plane is standard material. It's like a glass. And it's dark. I'm going to do a little bit darker. And the more important thing, it's semi-transparent. It has blending. So I'm going to put it half blending. Okay? It might something. I'm going to put it dark maybe. And I'm going to put half transparency. Okay? So what we are trying to do here is that when the light crosses this glass, half of the light is going to reach our eyes. And as you can see here, the white, the regular white, and the ultra mega white, because when they were rendered to the frame buffer, they were clamped, they have the same white. So when you add this plane here, and you do the blending, of half the color of this object, which is black, and half the color of the pixel which is drawn, what you get is the same color for both of them. Okay, because just so you understand what is going on here, we had a function like was something like this. One is white, the other is ultra mega white, okay? But we clamped the value here, so sorry, maybe more like this. This was white and it was ultra mega white, but we clamped it to 1, so they both have the same white. So now if you do an operation where you multiply by 0.5, this is going to be half of it, and this is going to be half of it. Although you know that if it was true, it wouldn't be this value. It will be half of this value here. So it will be something like this, okay? But because we lose information when we store the data on the frame buffer from 0 to 1, because we are using only 1 byte, we are losing that information and we cannot retrieve it, okay? So how can we fix this problem? Any suggestions or any ideas of how can you solve the problem that if I have brighter, I keep that information, I don't lose it? Any suggestions? Any ideas? No, nobody wants to write on the chat a possible solution to this problem. The most simple solution, the most obvious solution, the one that only will take changing a little bit my code. No ideas, no proposals, no suggestions. Come on. It's a very obvious solution. There's only one solution and it's super obvious. If you are storing data, go back again, explaining, if I'm storing data and I'm clamping the data and I don't want to clamp the data and I'm clamping it because I'm storing it in a byte, and byte has only 256 possible values and I don't want to lose the area that goes beyond the value, how can I fix this? Storing in more than a byte, okay? The obvious solution. There's no more other solution, okay? So if we have, I don't know, not 2 bytes, maybe I can reach more values so I won't lose this information, okay? the obvious. And obviously, when we are rendering currently in any to the screen, we have only 1 byte, so we cannot do that. But if we render to a frame buffer, we can specify how many bytes we want per color channel. And so here I can use it in my engine here. If I go here, I can say how many precision I want per color. By default is low, which is 1 byte, but I can raise it to half float or float, okay? This low, medium, high. So if I go to half float, you will see that boom, the object that was, the information was lost is not lost, it's there, the information, okay? You can see that it's not the same. When I see through this glass, even if this glass, I modify the material to be darker, okay? You can see that even in this situation is darkening this one, obviously, because this was white, but it cannot darken this one because this is super white, okay? And this is important when you have lights on a scene. There's a lot of lights on the scene, and those lights could be very bright. And because maybe when you are going to process the transparencies, or you are going to process it with other things on the future, you're going to apply any effects, you don't want to operate over data that has been lost, okay? So main important thing when you render is if you know there's the possibility that what you're going to render is going to clamp to 0 to 1 and you don't want to lose that extra data, the only solution is you work in HDR. How do you work in HDR? Instead of using 8 bits per color channel, you use 16 bits or 32 bits. If you do this, you have lots of more possible colors, okay? And if you have more colors, then that means that also, not only you have extra possible values that go beyond 1, also means that between 0 and 1, you have much more data. That means that you can do more interesting things on colors. There's more possible gradients, okay? So, and this also goes very in line with other topic, which is perception, visual perception. I already showed you this image some time ago in the first class. And the idea of this image is that this beautiful drawing by Petrus van Schendel, you can see how he understands that when somebody is close to a very bright light, the colors are, you can see more colors, greens, reds a little bit. Obviously, this is very yellowish because this light is incandescent light. But if you go to dark areas, like this area here on the drawing, there's less color changes. These are more grayscale. And this is because our perceptive way of detecting the colors only works when there's a lot of light. But also there's another problem when you have a lot of light, which is that here, for instance, we tend to assume that you can have a lot of red without green, but that's not true. If you have lots of red, you also have lots of green because red and green overlap. Okay, that means that it's very common error to think that if you go to your engine and you put a very, 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 very powerful light and you shine it to a red object, it's going to stay red. In reality, that's not the truth. In reality, it will happen something like this. When something is very, you put a lot of light, colors disappear. I mean, it goes to white, or it can go to, yes, it usually goes to grayscale. You don't conserve the colors because the whiter it is, the more you lose information. So here I can show you also this in a different way. Let me show you this in Blender, which is easy to see. So here in Blender, I'm going to go to the renderer here. Okay, so I have this light over here. I'm going to put it, I don't know, very close to this object. So let me go here. Yes, maybe here, maybe better. Yeah. So if I render this surface, there's a little bit of a specular. I don't know if you can see the specular. There's here a little specular. I'm going to go to the material, and I'm going to remove any specularity because I want to focus on only on the diffuse color. Okay. So this object now is gray, but I'm going to make it red. Okay, pure red. So now this object is pure red, and I'm going to remove any light from the scene that is not the main light. So this one over here, out. So this scene, this object is only lit by this light, which by the way is white. This light over here is totally white, okay? So it's obvious that if you multiply white by red, the color is going to be red. Remember that 111 multiplied by 100 is going to be 100. But if I go to this light, I click it here and I go to the power and increase the power a lot. I'm going to add a new 0 in power. Okay, it's still red, although the color is a little bit bluish. And if I go to beyond this, like another 0, it's starting to change the color. It's now purple. And if I add another 0, it's white. Okay, and this is important because if you do this in your engine currently, you will see that if you go beyond multiply any red object by a very high value, it's going to be a very high red. And when you're rendering, it's going to clamp to red, and you're going to see object pure red. And here, in reality, this is not like that. In reality, if something is very, very, very bright in like any of the channels, in the red, on the green, or the blue, it's going to be white. Okay, but we haven't modeled that. What happens that? I mean, we want to model this kind of effect that when something is super bright, you see it as white, not see it like very red or very blue or very green. Okay, and if we don't do that, we are going to have like a lot of errors when you have like daylight and nightlight and stuff like that. There is a change on perception. There's also another topic, which is exposure, and this is why most of the people want to use HDR, which is usually when you take a picture, our eyes has a very wide dynamic range. That means that our eyes are able to see at the same time very dark areas and very bright areas at the same time. Okay, but in reality, if you have experience with cameras, you will see that our cameras don't work that way. Our cameras are way worse than our eyes, and that means that the cameras, or they pick up the dark areas, but then the bright areas are white, or they pick up the white areas, but then the dark areas are black. Okay, they cannot pick both. That's why many programs or cameras or even mobile phones, when you take a picture, they take several pictures with different exposures. Remember, the exposure means how long you leave the sensor capturing light. So it takes two pictures, one with, or three pictures, one with lots of exposure. That means that it takes a lot of light, but some areas are going to be super bright, and then takes another picture very rapidly with low exposure. And because it has both images, it can understand which areas are overexposed and which areas are underexposed, and merge those two images together to create an image that looks better. Okay, if you've seen this, if this works because you expect that the image is not going to change a lot. If you try to do these images with like different exposures, like there's areas very bright and areas very dark on the same image, and you take the image and there's something moving, you will see how there's errors on the because the camera are taking two pictures in different moments, so they cannot match perfectly that areas that are changing. Okay, anyway, so it's hard to have in the same image very bright areas and very dark areas, and we want to try to mimic how our eye perceives this very wide range of intensities. Okay, so this is why most of the cameras, they talk about HDR and dynamic range, and there's formats like EXR or HDR, which are formats that are focused always on having like not very dark images or very white bright images, but try to blend them together to have a more like dark areas and bright areas without burning the colors, like information in the middle. Okay, and how can we solve this? Well, the trick is that we use what is called a tone mapper. A tone mapper is an algorithm that you can apply over an image that is HDR. This is very important. The image has to have a very wide range. Okay, it has to go from 0 to whatever intensity, and you apply this algorithm that is going to mimic how our eye behaves when we see the light. Okay, so if there is very dark, it's going to try to push the colors to be a little bit brighter, and if it's super bright, it's going to push them down so they are inside our spectrum. And as I said, this is trying to mimic how our brain or our perceptive system tries to work. So it's kind of complex to do this because, as I said, you cannot measure this. You have to just try to see from the perception point of view and try to make tests to see which one works best. Okay, so a tone mapper at the end is more like a post-processing shader. It's a shader that we apply at the end of the image when before we convert the image from from linear space to gamma space, and we apply the gamma space right after computing the tone mapper, and this tries to bring an HDR image, an image that has a very wide range of illumination, back to a low range without destroying the colors, and also trying to mimic how our eye works. Okay, this kind of implementation of tone mappers, you will see that there's like this kind of operations, and this is one implementation of a tone mapper I found on the internet. It has some control here, variables that you can play around with, like you can change these variables to see if it matches better your perception. And what they do is they read the color and they apply here some operations. You can see here that it does a dot product between the color and these numbers here. This is to try to bring part of the red and the green and the blue to the other channels, and also some operations that are very basic. It doesn't take too much computing power because this is more like changing a little bit like the coordinate system of one object. Okay, and after doing this, at the end they always apply the inverse of the gamma. You can see E gamma. So you apply the inverse of the gamma, and then you have the final color that you're going to display on the screen, and that's it. You don't apply any other algorithms on top of this. If you do that, you're going to destroy the quality. Okay. This is one implementation I found on the internet. There's other implementations, like this is the one that Naughty Dog, the creators of Uncharted and The Last of Us, they propose it. Okay, and you can see there's a lot of constants, and because this is more like a perceptive thing, so they have played around with the values until they found the one that works well, and you can apply it to see if it looks better. Okay, there's another one called ACE that you may want to try because it's also very famous on many applications. Most engines, by the way, if I go to Blender, here, if I don't recall correctly, there's here color management. So here you can see different functions to apply, as I was saying before. Okay, here you can say that it's always working as sRGB. Okay, and also that you want to transform using different functions of different tone mappers depending on what you want to achieve. Okay, and you can see if I didn't do the one, but it would look like this, and a different one: filmic, logarithmic, raw. Anyway, okay. So depending on this, it's going to treat colors totally different. Okay, as you can control exposure, how time the camera is open, and also which kind of gamma you want to apply to this light. Okay, so now you understand better what's the linear space and what's the HDR. Okay, linear space is to convert from gamma to linear, and HDR is try to store things on more than 1 byte, so it looks better. And if you also want to mimic better how our eyes behave, this is another algorithm I've seen many times. I have implemented myself in one of my engines, which is if you are in a dark area, your eyes will try to open more the pupil, so there's more light going inside, so you will see brighter. But if you go to a very bright area, it's going to first be very annoying to you because your pupil is very open and it's going to close to absorb less information, okay, less light. And this is easy to achieve. You only have to compute how much light do you have on the screen. At any moment, if it's too much, you multiply the end color by some factor because you are reducing the amount of light that enters in your sensor. And if there's less information, you open a little bit, okay? But as I say, this is for mimicking how our eye behaves. If you want to do in a shader, at the end is something like this. But you need to know how much light was on the previous frame, which is not easy. You can do this by doing the average of some of the pixels of the previous frame at the end, and then using that information to construct some value that you pass to the next one. Okay. So by the way, I already implemented this feature some time ago on my engine. So if I go here, maybe you can see it. Sorry. You have to compile all the shaders. That's why it takes so much time. Yep. Okay. So let's go to the player. Play. Sorry, it starts to compute a lot of stuff. Yeah, now. So here you can see I'm watching an area that is very bright, sorry, very dark. So I see everything looks more or less fine. But if I go to this area, which is very bright, I don't know if it's enabled now. Yes. Well, I don't know if you can see it. At the very beginning, it's very, when I see something that is very bright, if I go back to the dark areas, they are a little bit darker and then it gets a little bit brighter. You can control how much do you want to. In this case, I have a function here to control the range of this. And so in case you want to see how I compute this, what I do is I take the final frame. Let me show you. I compute the average and I clamp it and I smooth it over time and I apply it as the value of my tone mapper to define how much do I want to. And this average I computed using this frame, the current frame. I'm using the current frame. Some people use the previous frame. I use the current frame. Okay, so I pass the current frame after applying the glowing, and I compute the average, and then I clamp it between 0 and 1 because I don't want this value to be too big. And indeed, I can play here with some of the values, I think, but anyway, I don't want to do that now. Okay, so it's interesting because that mimics a little bit better how our eyes perceive. If I go here, for instance, let me show you. I'm going to go here. I'm going to get so here 1 second. So here you can see now I'm a very bright area, and if I go to dark area, no, it doesn't look very much because I think I clamped it too much because it was too exaggerated and it was annoying to see. But anyway, it's always easy to have this kind of implementation. You want to mimic better how the light perceive it, and that's mostly it. So From the presentation, I think there's no more slides, maybe a couple of slides more about how to implement this. So this is the pipeline on our current state. If everything goes well, we collect all the render calls, we generate the shadow maps, we generate the gbuffer, and then we compute the illumination pass where we use the shadow map and the gbuffers to compute the final image. But this image now has to be HDR, very important. We don't want to waste any information. Also here we have to compute everything in linear space. And then here we pass the image in linear space HDR to this shader, which is going to render a full screen quad, and is going first to apply the tone mapper to reduce this big range of illumination that goes from 0 to whatever to 0 to 1. And it's also going to apply the gamma to be sure that we have the image as the monitors wants to see it. Okay? And that's mostly it. So just to show you a little bit of code, because I know that you want to see code. Currently this is the implementation. This is my implementation, or this is the default code. No, this is my implementation from the other day. Okay. Here you can see the other day when I was working on the renderer that I was rendering. Let me see, render the ferret. I'm going to only explain on the ferret, but also what I'm going to explain now applies also on the forward. So the other day we have these gbuffers, FBO, and we render inside them the scene, and then we render all this information to the screen. Okay. But I want to have another thing besides the FBO. When I was rendering this the other day, I say that it would be nice to have another FBO called illumination FBO. Okay. So when I create this FBO, I'm going to create also another FBO, call it illumination FBO, because I want to store the data not directly to the screen. I want to store it first inside the buffer in a texture. Then I'm going to transform that at the end. Okay, so I'm going to store here. I don't need 3 textures. The illumination FBO, we only need 1 texture. Is the image that we are going to display on the screen. We don't need alpha because we are going to store an image that we're going to display on the screen. My screen doesn't have alpha, obviously. So RGB. And here is the important part. I don't want to use one unsigned byte, because an unsigned byte means that I'm clamping to values that are beyond 1. I want more. So if I want more, I can use half float. Okay, so half float here. And as I don't need, even if I don't want to have the def buffers, if I don't want to. Anyway, now I have the G buffers, but I also have another buffer, an FBO, that only contains 1 texture, and this image can store very high values. Okay, so now is the time to test it. So once I have rendered all the G buffers, I'm going to enable this one. So now I'm not rendering to the screen, I'm rendering to this FBO. And at the end, when I have finished everything, I'm going to say unbind. So now I have an HDR image of my frame, but it's not visible. Okay, so here I should say, if everything goes well, I would like to show this on the screen. Remember, if I don't show anything to the screen, if I comment these 2 lines, sorry, it's not here, it's color texture 0. Okay, if I don't show this, because now I have stored the result image on a texture and I'm not displaying that texture on the screen, when I execute this, I won't see anything. Okay, so I don't see anything because I have the image, but I'm not showing it. It's stored in a texture. I can see if I go here to textures and I scroll down, the image is here. Okay, if I move the camera, I'll go here to the camera and I move the camera, the image is here in a texture, but not on my screen. Okay, so the next step always is I want to show that here. Okay, I have here this code that shows the gbuffers. I put it, if I'm not showing the gbuffers, I will show it this. Okay, so if I do this, I have exactly the same as I had before, with the difference that when I compare this image, I had values that go from 0 to very high values. But I don't see the difference here, because if there's any value that goes beyond 1, and there's not many things here. Maybe these parts here are beyond 1 probably, and yeah, this point here, this area here are probably beyond 1, but here my scene, everything goes to from 0 to before 1. Okay, I can exaggerate it. I go to the spotlight and say, no, my spotlight is super bright, and if I do this, yes, these points here, they are way behind, above 1. But it's okay. I mean, when I render this image to my screen, to this screen over here, it looks the same as it would look if I wasn't using an HDR FBO, because I'm not operating. As I said, using an HDR makes sense if you're going to operate, but I'm not operating. I'm not doing any operation mathematically with the pixels, so it's the same as using this one, or if I use, instead of using this one, I use one that is only like unsigned byte. If I do this, is exactly the same, because in this case, at the end of my render, I'm not doing any operation. So you can see, if I go back here, it's exactly the same. And if I go to my spotlight and I decide to put the spotlight super bright, it's exactly the same. But we want to operate. So we put it back to half float, and we want to do something with this image besides showing it to the screen. For instance, I can apply a tone mapper, okay? That's one of the options. So let's do that. Let's apply a tone mapper. In this case, I will need to have a shader. Okay, oh, there's also a shader there, so it's okay. And it's going to be, let's call it tone mapper. Okay, so I'm going to take this shader and I'm going to enable it. And then I'm going to render this image with this shader. Okay, I have this like enabling because I'm going to have to pass some values to the shader. So assuming that we have this tone mapper here, let's go to my shader atlas and create a very simple tone mapper. So for now, remember, I'm going to render this, means I'm going to render a quad. So we need to use the quad VS because we don't want to apply any operation. So I don't know, let's go here and say I have a tone mapper that uses the quad vertex shader because we don't have model, we don't have, this quad is going to be rendered on a screen space, and here we are going to call it the tone mapper FS. Okay, so what I'm going to do is I'm going to search, always I like to search for the texture one because it's the simplest one here, and I'm going to rename it to tone mapper here, tone mapper, and I don't need any of these positions, normals, colors, whatever. I don't need any of this. Okay, but what do I need is, first I need to render, like read the color from the buffer. Okay, and I'm not going to do anything. I'm going to read the color, okay, from this texture, and I'm going to show it on the screen, nothing else. Okay, to be sure that I'm not breaking anything. So this shader is not going to do anything. It's going just to read the texture and show it on the screen, so I can show it to you. And if I execute this and everything goes right, I should have this image here that is exactly the same, nothing changed. I can go to my spotlight, put it very bright. Okay, it's exactly the same. But if my shader, sorry, I'm going to execute it, leave it executing because I want to modify the shader. If, let's go back here, I'm going to put the spot back again to very bright. Okay, if my shader, here, this shader, I operate here, imagine I take this color and multiply it by 0.5. Okay, if I go back here and reload, you will see that here this area, which is very white, I have lost all the information. But if I multiply by 0.5, I'm going to reload now, 3, 2, 1. You will see I get back some of the information I had before. If I go even lower, I can see the information is still there, because even if it was clamped, like, sorry, it was above 1, if I multiply by 0.1, it goes below again. So you can see now that I can only see the dark areas because I multiply everything by 0.1. But obviously, if I try to do this and I wasn't using an HDR, I was using a regular buffer with an unsigned byte, obviously, because I have clamped the values. If I multiply this, even if I go now to the spotlight and try to make it very bright, you will see intensity that this is what happens. Okay, and I'm multiplying a white color by 0.1, so the maximum possible value is 0.1. You can go beyond that, so you can see that you almost cannot see anything. Okay, so as I said, super important always to render to a HDR. Okay, and now if I wanted to apply the tone mapper, for instance, I can do it now because it's just a couple of lines, so it doesn't make much sense. So let's take this one. I don't know if this is a good one or the worst one. Let's take this one. So I'm going to go to my shader, put it here. Super crappy shader. Sorry, I'm going to, this is for the old version, so I want to keep this flat color here. Yeah. Okay, oops. So this shader here, it requires to have these values, okay? E scale, average loom, loom white, and E gamma. E gamma is assuming that we have work on linear space. The problem is we are not working on linear space. Anyway, I need these 4 values, and they are 4 floats. So let's go to my code in C++ and pass this data here. So in this case, first, scale. Scale, I understand, means to multiply the final color by something, okay? So instead of just putting the values here, I'm going to put them global. Like in this case, I'm going to put tone mapper scale, and I'm going to put these values, I don't know, maybe in the renderer, although it's more like a FX, but anyway, I can put it here. So I'm going to put these values here, the tone mapper scale. Which else do I have here? The average loom. Although the average loom should be something that you control from, oops, average loom white. And the final one is E gamma. Although this one, it should be 1, but anyway. It should be gamma, not E gamma, and I will do the inverse afterwards, okay? So I have these 4 values, and I need to initialize them always in any application. So go to your constructor, and put these values here and say the default values. Because I don't know the default values, just go with 1, 0 on all of them. Average loom, loom white, and I don't know, I guess that will make more sense. And because I have these 4 values, it's always good to have an UI to play around with them. So I'm going to make here my own UI to work with these ones. Because this is a slider, I think it's like slider probably. No, I don't know how to make sliders. 1 second, it's in the editor here. A slider, yeah, a slider flow, this one over here. So 1 second. Yeah, no, here, no, sorry, here, show UI. So I want a slider for this one, tone mapper, whatever, and it says from 1 to 1, I don't know, from 0 to 2. I don't have any idea. And let's go for the rest also. Average loom, loom white, and gamma. I don't know, between 0 and 1. I don't know if it makes sense, but anyway. So this is going to be tone mapper scale, average loom, loom white, and gamma. Okay, so now if I play with these values, I can modify them on the shader, which is like easier. So I'm going to put here these things. Okay, and so here for this one is going to be average loom. The next one, okay, is gamma. 1 divided by gamma. See, I didn't store the gamma. I stored the inverse gamma. I stored the gamma, and then I divided here. Makes more sense. And here the loom white. 2, and that's it. I think I have everything. Let me what's complaining here, because this has to be a float. Yeah. Okay. So let's try it. I think I saved the shader on the. Is saved? No. Okay. So now I have a way to test how it would look with this situation, these values. So I have my scene. I'm going to just burn it again because it's like nice to have something that's very burnt. And I go to my rendering, and here I have these values. And let's try to see what happens if I play with this value here and the average loom. I'm going to leave this scale to 1 because it means, so here you can see that I'm trying to, there was areas that were burned, and you can see that playing with this value, I managed to, they are not burned, but I haven't make the other areas darker. Okay, you can see if I play with this, they are not modifying this, only modifies the very bright areas, okay? And the average loom, I can play around here. And as it's limited to from 0 to 2, but if I go here and say 4 or even 10, you can see that now, and this is interesting, the dark areas are still dark, but the bright areas are not burned. Okay, if I go here, even if I reduce the intensity of this light, you can see that it's not destroying the illumination as destroying before. Okay, so this is nice. This means that my render now can have areas that are super bright and still it tries to keep the colors. Okay, which is part of the idea of using tone mapper. But also maybe you want to burn them or stuff like that, and I think that this here, if you play with the values, you can reach the values that you need. Okay, I don't know. Okay, so you will see always that every engine has a tone mapper, and even they have several tone mappers, and allow the users to choose the one that they feel more comfortable with, and that implies that the colors are going to look better. Just to remind you that I'm not using the gamma, so still the colors are not perfect. If you apply the gamma, they will look much better. Okay. And I think that's it for today. It's linear rendering and gamma rendering in a nutshell. And so that's more or less everything that you have to do. So this week, this you can code this, the tone mapper and the gamma correction and the HDR in, I don't know, less than a day, in like 3 hours, 4 hours. This is very simple. The PBR is a complex part. But the important thing is that you put the PBR, you put the linear rendering, and you put the HDR, and with the tone mapper, you will see how the scene starts to look way better. The colors will look much interesting, and when you play with the values, you will see that they obviously don't get burned or they don't look bad. Okay, so well, it's more realistic. Okay, and that's it. That was 1 hour and a half. So remember, for the next week, I will expect you that you have the PBR working at least in G buffers in the ferret. So try to come up. Oops, sorry. Try to put everything right on your current pipeline, at least in one of the options. Otherwise, you will have problems when you try to put everything together. Okay, and that's it. No questions here. See you on Monday on the class, and please come with something already done. Don't come with like starting the PBR, because next week we're going to start a totally different topic, which is how to make the illumination, the dark areas look better, when some kind of shadow for ambient, and that's totally different algorithm. So that means that you better have totally knowledge about what you have already done. Okay, cool. That's it. Thank you very much, and see you next day. Bye.